Right. Quicksort is the quickest sorting method for large data sets. Okay? It is a recursive method. Okay? When we start, we call the function like this. We specify a lower position and an upper position to work with. It doesn't actually sort anything. It's what we call a partition sort or a radix sort. Okay, what it attempts to do, it picks a number. There's been lots of work done on this, and you could just pick the middle number. All right, but that takes time because you've got to work out where the middle is. All right, so let's say we pick the middle number. What the whole thing that Quicksort tries to do, it just says, right, okay then, I'm going to rearrange this list, and you'll think, God, this is doing a lot of work. I'm going to rearrange this list, not so that they're in order, just that everything to the left of 57 is smaller, and everything to the right of it is bigger. That's how Quicksort works. That's what it does. And then what you do is you say, right, well, then I've obviously got two lists that need sorting, and it does the same process again until you get down to a list that's got one item, and Quicksort says, well, actually, one item is in order. All right, but you'll see this working. But there's been loads of experiments done to say, right, does it matter which number you pick? You don't know anything about the numbers, so it doesn't. So what we're going to do is we're just going to pick the first item in the list as what we call the pivot value. Okay, so we're going to do Quicksort 1 to 11. So we're going to create 3 pointers. The pivot, which we denote with a P, that is the number that we're going to separate this list by. So we want to create two lists, one that's got numbers less than 15, which there aren't many of, and one that's got numbers bigger than 15. Okay? Right. We also have a left and right pointer, which we set to the values that we've been told to work with. Okay? Now what we're going to do is we're going to keep comparing items at the 2 pointers and move in towards the center. We're going to stop when they're all representing the same location. All right? It's easier to actually describe the process than it is to do. Right. So we look at our two values. Are the two values at the 2 pointers in the right order? Yeah. Assuming we're going ascending. Yeah, they are. So what we do is we move the pointer not associated with the pivot, i.e. the right one, in. And we do the test again. We say, right, are the two numbers at the left and right pointer in the right order? Yeah. Move the one not associated with the pivot in. Do the test again. Okay? 41 and 15, they're in the right order. Let's move the one not associated with the pivot in. Okay? I've obviously picked a ridiculously naff set of numbers here. The order I've put them, it doesn't matter. Okay, again, keep moving it in if they're in the correct order. Okay, right, we get to this setup. They're not in the right order. So we're going to swap the two values over. So 14 goes there and 15 goes there. The pivot has to stay with the number that we started with. So that goes and stays with the 15. We move the pointer not associated with the pivot in, which is now the left pointer, because it's all on its own. So it moves in. Are they in the right order? No, so we've got to swap them again. Okay, so the 21 goes there, and the 15 goes there. That's the pivot value. We move in the item that is not associated with the pivot. So the right pointer comes in. At that point, they're all referring to the same location, so we stop. Okay? So even though the numbers are weird, everything to the left of 15 is smaller, 14, and everything to the right of 15 is bigger. At this point, we would run Quicksort twice. we'd run Quicksort with 1, 1 to sort that part of the list, and we'd do Quicksort 3, 11. Okay? So we'll explore. There's no point in doing this one because one of the stop conditions for the recursion is if the left and right value are the same, stop. Okay, so that one would just go stop. Now, you might think, blimey, that was a lot of work to get down to a single item, which we then run a subroutine on the back of. But as soon as I do this, I have got the facility to use more than one processor. Okay, so if I've got 2 processors, these 2 operations can carry on independently. They do not overlap. There is no data to be shared. Okay, that's a separate list, that's a separate list. They're different bits of memory. So it meets the requirements for parallel processing, that you have not got memory dependency. Yes?
Well, it's the same.
It's the same.
You need multiple like memory controllers or something.
Oh, no, because you interleave it, don't you? Yeah, your memory management chips will interleave requests from different CPUs. All right? Moving the pointers doesn't require access to memory. Doing the comparison does when you grab the 2 values. You could speed it up by just holding the pivot value in a variable as well. So you're only actually ever looking at one memory location at a time when you do the comparison. So there's loads of things you can do, but it meets requirements of they are effectively separate lists. So you can have these processors working on this memory. They don't have to rely on each other. There's no issue with, oh, are you using that memory location? I'll wait for you. There's none of that. It's like, right, we can blast off and do this. Okay? If you've got a supercomputer that's got 100,000 processors, and the Quicksort with big data sets can get down to that sort of sizes of subroutine calls, you can take advantage of that. It's super scalar. This is awesome algorithm. Right, let's run the Quicksort again now with the 311. Okay, so that location, they've been sorted out. So we're going to run this instance of the Quicksort. Let me rub all that junk off. Again, in the exam, they will not give you a massive list of numbers to say, Quicksort it. They won't do that. They'll say, go through the process 3 times. So they'll have like, you've moved the pointers 3 times. Said what you've done as comparisons. Okay, right, so we're running Quicksort with 3. So the left pointer goes at 3, and the right pointer goes at 21. I'm going to change some of these numbers. I'm not going to break what I've got, because that's just going to be silly again. But what should we have? So 55. 55. I'm going to change it to 55. Yeah, still finger. Right. We're just going to pick the first item at the left pointer as the pivot. Okay? And we're going to do these comparisons again. Moving in the one that isn't associated with the pivot. So, 55 and 100, no, they're okay, they're in the right order. Let's move in the right pointer. So we're bringing the points together. Right, 31 and 55, they are in the wrong order, so I'm going to switch them. 31, 55. The pivot has to stay with that 55. That's the only thing you can mess up when you're going through this. Okay? We then move in the left pointer. Okay? If you write it down like this, the pivot is the pain. But if you write it down like this, you can show how the left and right pointers have changed. Okay? Right, compare again. Ah, they're in the wrong order, so we've got to swap them back. Okay, the pivot's now gone back over here. And we move in the right pointer. 41 and 55 are in the wrong order. We've got to swap them again. So it looks like there's lots of activity going on. But I'll show you on the computer-written JavaScript programs to do this. To show you how much quicker it is compared to insertion sort and everything. Once you get loads of data. Right, moving the pointer that's not associated. Oh dear, the 76. And the 55 are now the wrong way round. So swap them. Okay, move in the right pointer. Do the comparison again. 55 and 50, oh, they're in the wrong order. I'm going to wear my fingers out. Move in. The one not associated with the pivot. Oh, bloody hell. I picked the right good number there. Right, 55 and 57 swap. Okay, pivots come back there. Right comes in. Okay, they're in the right order. I haven't got a swap. So I'm moving the pointer not associated with the pivot and we stop. Okay, so we had a list, 3 to 11. So all the items here should be less than 55. All the items here, unless I've cocked it up, should be greater than 55. So it's actually a really simple process. The algorithm's quite nasty. And most quicksort algorithms that I've seen in books have got errors in them. Okay? Because you've got to check for overlaps, going off bits of list, and all sorts of things. The algorithms tend to not bother with those sort of details. Yes, Gibbs? That's the same issue that we talked about before with the tree. In general, we're talking about identification numbers, aren't we? Unique numbers that we're sorting. So these are like record IDs. Yes, Nathan? Or is that just to go?
Sorry, yeah.
Yeah. Nathan's yawning for those people that can't see watching the video. He's got his arm up like this. He's going like this. Okay. Right. So when we get to that point, we put 55 in the correct place in the list. And we'd run quicksort again, but this time it would be from the bottom position, 3, up to 1 less than where the pivot was, which was 5, and we'd run it again with 7 up to the top position. And they would run independently. But you can see that every time you run one of the quicksort subroutines, you generate 2 quicksort subroutines. So you start off with like 1, that generates 2, that generates 2. So by the time you've been through 2 passes, or full passes, you've called quicksort 4 times. It's funny, I did that as one of my projects. I did a project on data structures for my computing A-level, and one of them was drawing dynamic binary trees. But the interesting bit was trying to get it to fit on screen properly when they got deep. And it folded them and all sorts of stuff. And it was on a BBC, 32K of RAM. Okay. Right, so that's the premise of quicksort. So you just keep going until you get down to a list which is a single item, and then you can stop. So it doesn't actually ever sort anything. It's just pushing stuff left and right of the pivot value. That's all it does. Okay. Yes, Richard.
So if you speak to the 7-Eleven one.
7-Eleven? Well, the drugstore. Yeah, right, go on.
So if you do left on the 7,
Yeah.
right on the 11,
Yeah.
you would swap the 2 values, swap on the pivot point as well, and all of them would match after that.
Right, so let's just do that. So we'll do the 7-Eleven one. That's going to be the pivot. I'll do it quicker. Right. Not in the right order, are they? So we're going to swap. Pivot goes over there. Moving the left pointer. Ooh, right order. Moving the left pointer. Moving that. So it's actually quite quick. When all you're doing is you're changing a pointer, which is just adding or subtracting 1 from an integer. The quickest operation the CPU can do. Alright, ultra quick operation.
And then would you run 7-11, 7-10?
Yeah, you'd have to run 710 because you don't know about the numbers in that part of the list. But there is no right-hand list in that case, is there? Because you're at the end. Okay, yeah, you'd run 7-11. Quicksort 7-11. 710, yeah. Yeah, if you do 7-11, you've written a really bad bit of programming and you're just going to screw the whole thing up if you write code like that. But some of the algorithms are like that in books. They break. Okay.
So would you wait until you've got like with quicksort, you know, like 311, it's only comparing 8 numbers.
Yeah.
So then, would you say if you've only got 8 numbers, use insertion sort?
Exactly. Right. The literal quicksort goes all the way down. I don't know what effect that has on the webcam, that going into that mode. I bet it jerks it or something. Right. If you're doing the traditional quicksort, you go right down until you get a single item. But there's a lot of work in moving those pivots. So what you'd actually do, once you get down to about 10 items, you say, right, if the length of this list is 10 or less, run insertion sort on that list. Because the insertion sort can just work on a group. Okay, you just specify what the upper and lower bound is. And it's by doing things like that where you get hybrids, where you can really get mega speed increases. Okay. Right, I'll stop the vids there, and I'll show you some JavaScript code if I can find it.